just call it legend, or that part for you. And you will talk about unicorn paths and combinatorics of curves on surfaces.
Okay, thank you very much. First time in Athens, Georgia. Really enjoying it. It's such a nice place. Thank you for inviting me. So throughout S is going to be a surface, G is G, and P boundary components, because I want arcs. Okay. And complexity of S is some number 3G plus P minus 3. This is just basically the number of curves you see in the interior of the surface when you take a opacity composition. So a curve of S is an isotopic class. Simple closed curve on S that is not homotopic to a point or into the boundary of S. Okay. So I talked about them last talk. An arc of S is an ambient isotopic class of properly embedded interval in S that is not homotopic into the boundary.
Can the ends move on the boundary?
Yes, ambient isotopic. Ambient isotopic. Yes, so you're allowed to move the boundary. Okay, so for example, what's not allowed is an arc like that. That's, yeah, so that's a non-example of. Okay. So curve graph. C of S has vertices, curves of S, and edges whenever there exist disjoint representatives of the two classes. So we saw this last talk. And you can define the arc graph A of S as well. So the vertices are arcs of S, and edges, again, disjoint routes. And then you also got the arc and curve graph, so all three are going to play today. Probably can't see that, so put it up there. Arc and curve graph AC of S when the vertices of both arcs or curves. Okay. Right, so the talk is about the coarse geometry of these graphs. Okay. So Tariq showed you some applications of them, so they're interesting graphs. But today I'm just going to get on with the proofs and the theorems. That's all I want to do. And the first theorem I'm going to discuss in the first half of the talk is the theorem due to Masur and Minsky. And the first draft of this result came out in 1996. Okay. And it states that there exists a delta that depends on S such that the curve graph is delta hyperbolic. Okay. So just a reminder what that means. It means for every geodesic triangle, G1, G2, G3 in the graph, so G1 is in the delta neighborhood of the other two sides. picture is this. And this one's G. Okay, so here's a note. The inclusion map from the curve graph into the Arkin curve graph is a 2-2 quasi-isometry. So AC of S is also hyperbolic for some delta. Right. Next theorem I'm going to discuss today is due to Masur and Schleiner. And I think the first draft of this was in 2010. And they say that there's some delta that depends on S, such that the arc graph is delta hyperbolic. Okay. Right. They also prove many other graphs are hyperbolic, such as the disk graph for a closed surface. Right. Okay.
So this graph, is that for a closed surface in like 3 manifold or something like that?
Yes, I think there might be some things you want. But for example, hand body, that's definitely going to be hyperbolic. The first thing I'm going to do today is this some delta, some universal constant. Such that the arc graph is delta hyperbolic. So this constant delta doesn't depend on S. And we'll also get that the curve graph is a delta hyperbolic as well, for some uniform delta. And this is often referred to as uniform hyperbolicity for these graphs. Okay. So the curve graphs being uniformly hyperbolic was also proved by Terry. Sorry about this noise. So Terry just proved it. Brian Bode just proved it. Matt Clay, that's around for Hensel Schleiner. Sorry, Saul, we've not approved your name. Okay, this talk is.
Need to break the shirt.
Maybe.
Is the bonus paper appear?
It's on his webpage. So if you want to find any paper of his, it'll be on his webpage. He doesn't put things on the archive. Okay. Right. Okay. So let me first discuss the archive. Okay. And I'm going to tell you what a unicorn path is.
So do you also get uniform velocity for the arc graph? Arc and curve and curve.
Oh, that's hard.
Oh,
This is the, sorry, that's really interesting.
I see.
Should have just wrote A. Yes, it's just the arc graph. Right, okay. So I'm going to describe to you what uniform paths are. So suppose I've got A and B arcs in S that cut. Okay? So what does cut mean? It means it doesn't exist. It does not exist as representatives. So basically they intersect.
Well, we know what the number is, isn't that, that's part of the interesting thing here.
Yeah, so you can get a low constant for the thinness, constant hyperbolicity. But today I'm not going to do all the details of that. I'm just going to give you the short proof of that they're going to be hyperbolic.
It's less than 10, right? It's very small.
Yeah, so you can say the thinness constant for the arc graph is 7. And the thinness constant for the curve graph is 17.
Oh.
That would be right.
It's 17.
Sorry?
It's 17. I couldn't remember
Yeah.
your curses.
Okay, where was that? I'm going to try and motivate this by a picture. I'm going to draw a picture of A. Is A. And I'm going to pick preferred endpoints of my arcs. A plus and A, B plus and B. Okay? And this endpoint is going to be A plus. A is red. Okay? And B is going to cut A, so it's going to come through many times. And hit A. Okay? So this is a really local picture at the moment. Now one of these arcs is going to go up to the boundary and have an endpoint B plus. Okay? So I want to tell you this path from A to B, which is going to be in path. So, so I'm going to call this path V. It's going to be parameterized by Vi. And V0 is going to be A. Okay? And then we draw a picture of what V1 is going to be. And V1 is going to be the arc where you start at B plus, and you go along B until you hit A. And then you go towards A plus. Okay? And that'll be an arc that's not homotopically bound into the boundary. It has that. And I'm going to call this B1. And now what's B2? I'll tell you what's B2. Okay, so you start at B. And if you follow B, you might go around the surface a bit, and then it'll walk around. And then eventually you'll cut A. Okay? And then you go to A plus. So that is U2.
So that's the third time you did it. The fourth time you did
Oh, sorry.
That's
I meant
before.
the first time I hit the subinterval of A,
Oh, I see.
that is contained in V1. Apologies. You should just, yeah, the picture will communicate better now. And then V3, well, I guess. You'll follow B, and then you're looking for the first time you hit the interval overhead. So you're going around, maybe. Then eventually you'll come and hit it, and then you go to A. So this is a path by the picture. And eventually you'll run out of intersections with B. So eventually you'll get to B. And that's what a uniform path is. Right. So let me write that down. Can define P of A plus P plus to be the set of arcs represented by A prime union B prime, where A prime is a subset of A, but also the end point of A is in A prime. So you want subarcs of B which contain the endpoint B plus, the preferred endpoint. Okay, and these, I think they first appeared in Hatcher's work. He proved that the arc complex is contractible using this surgery argument. Okay, let me do a concrete example. Rather than giving an abstract definition. So,
And these are partially ordered by like this part of A and A producing.
exactly. They are. So, whenever you're further along towards B, you'll have more of the arc of B and less of the arc of A.
By the way, someone had to explain to me that unicorn means one corner.
Yep,
That
thank
was
you for that.
useful, yeah.
Yeah, so
You just
uniform
use it
means,
for its whimsy.
so I like this example. So think of the Riemann sphere, there's a point at infinity, and there's an intersection point between them and blue. Okay, and there's some boundary components missing. So these are two arcs, A is red, and B is blue. Okay, and I'm going to choose these preferred endpoints. Okay, so A will be, you know what, let me draw V1. Well, I start from the blue guy, hit A, and I go to A plus. That's V1. What's V2? I start with the blue guy, I keep going until I hit that sub-arc of V1 containing A, and then close up. So that's V2. V3. Keep going. So V3 cuts V1, that's fine. That's V3. And V4 is in blue, so it's a rainbow uniform. Okay, so that's an explicit example. Then that. Okay, so I told you what PA plus B plus means. So suppose I got three arcs now, and three preferred endpoints. So the lemma is this. In the arc graph, these paths form slim triangles. Not geodesic triangles, but slim triangles. Okay, so the lemma is that this side is contained in the one neighborhood of the other two sides. Let me prove that. So given some uniform arc in this path, draw a picture. Okay, so V is just some arc of A, and just some arc of C. Okay, is A plus, is C plus. And now we draw B. Okay? Now if B is disjoint from this arc, then we're done. If B is not disjoint from this arc, then it cuts B. Okay? So you draw B, and it will hit this arc somewhere. If it hits it in this part, then close it up. Okay? And this arc is in this. Okay? So that's the proof of this. So if you have any questions, just don't be afraid to ask.
So this has no assumptions, right? Surface and anything. Right.
Yeah. So it's a hyperbolicity criterion of Masur and Minsky, and Combinatorics is a nice proof of it as well. Okay. So this is the criterion I'm going to use. Suppose G is a graph, and K is an integer. Okay. And for all x, y in the graph, there's this some connected subgraph such that x and y are in the connected subgraph. So this is a really nice criterion, by the way. I'm going to say this is a subgraph. So it doesn't have to be a path, it could be just some subgraph. You need it to be connected, you want x, y to be in it. When the distance between x and y is small, then the diameter of x, y is bounded. That's important, because I don't want to take the whole graph every time, for instance. And the last condition is you take this connected subgraph between x and z, then you get, there's a condition, slimness. And now I've got no room for the conclusion, so put it over here. So that, connecting it to here. Then G is delta hyperbolic, where delta only depends on K. Okay. Right, so now proof for the arc graph being uniformly hyperbolic is you take LAB to be the union of all four unicorn paths. Okay? Right. If A and B are disjoint, just take so if A and B take all four unicorn paths, there's four because there were four choices of endpoints, two for each arc. And you get, by this lemma, you can take K equals 1 in the criterion. And that's the end of the proof.
Why is this epsilon usually? Why is that in the
Epsilon?
No,
sorry.
Yeah, that in something. Oh, it's in that. Oh, sorry.
It's
yeah.
in
the one.
Yeah.
Okay.
Why is it in there? Because and you know the first time you hit the green arc, which is like a C.
That arc is a unicorn between A plus and B plus.
yeah, so this is a bit of B,
You don't get to turn every time you hit. You don't always.
this is a bit of C.
That's the first time you're hitting. Oh, is that the first time you're hitting C, or the first time you're hitting that arc of C?
You're hitting one of those two arcs.
First, I see. Yeah.
Yeah.
Yeah, that's right.
Does it even have to be first?
So this is B plus.
No, wait. Why
It has
don't
to
you
be
keep them
first.
both first outside the picture?
This has to be first. Otherwise, if I keep going,
Oh.
then I might intersect it, and then I
Oh.
don't get one.
Right. Why can't the first time you hit the green C be outside of this picture?
Sorry, I hit V. Sorry, so I've got C prime inside B.
Yeah.
So C prime really is a subarc of C.
Yeah.
And I'm looking for, and I also got an A prime over here, a subarc of A.
You're saying the first time you hit C prime is
Right, the first time I hit either A prime or C prime.
right.
And then depending on which I construct.
That's not the first time you hit C.
No. It's the first time I hit B.
Yeah.
It might not be the strength of C, it's just the strength of this B.
Yeah. But that's not. It's not a unicorn path unless it's. Not every one corner path is.
Yes, but it's an arc
Yeah.
represented by a properly embedded interval, which is a subarc of B and a subarc
Yeah.
of C. So it's uniform.
Okay.
That's all.
So it is uniform. That's the definition of the So if you have any, so please ask more questions. Okay, so I'll now prove that AC is AC versus uniformly hyperbolic. Okay, and to do this, I'm going to define something. Suppose X is the vertex of AC, So x is either an arc or curve. Okay. Then define a of x to be either, or just a set x if x is an arc, or the set of arcs A such that A is type form x. X is a curve. If you have any questions.
Can you read it first
then-
again?
Sorry?
What's A of x in the second? I didn't hear.
Which bit?
The
Is it
second bit.
The second bit. Okay, so if x is a curve,
Mm-hmm.
I don't want a curve, I want arcs.
Right.
So I take all the arcs that miss x. Okay? So that will always be non-empty from the surface of boundary. X, so if x is a curve, let this be the set of all the arcs that is one. Okay, so the picture really is, oh, I'll draw a picture there. I'm going to tell you what preferred paths you want to take, preferred subpaths you want to take in the arc and curve graph.
Sorry, it's a single arc or it's not all arcs? Or
It's all arcs. All arcs. Yeah, all arcs. So curly P next to Y is going to be the union for A and A of X, or B and A of Y, all the uniform paths that you can possibly get. Okay? So now I'll draw the picture in the graph. So this is a picture in the graph. I have,
So this L is the L from the proof of
yeah, it is.
this thing?
Yes, yes. Yes, I'm keeping the same L as I chose earlier, which might be confusing, but whatever. Okay, so the picture is so if x and y are curves, take all the arcs adjacent to x and look at the paths, uniform paths I get. So there's just, it could be infinitely many, for example. Okay, now slimness is going to be 1 again. And that's not too hard to show. So that's fact 1. Fact 2, well-bound diameter. Well, if x and y are adjacent, then the diameter in the arc and curve graph of P of xy is at most 5. Okay, so let's just prove that fact right now. If x and y are curves, say, suppose these are both curves, that is disjoint. Then there's an arc that's disjoint from both, so that's needed. And then you've got some other, just any other arc, AX, some any other arc, AY, containing these big capital things. This is X, this is X, so the uniform path between these two is completely disjoint from X. The uniform path between these two is completely disjoint from Y. This is a bit of a mess. And then, so remember, this thing is all the uniform paths connecting some mark here and some mark here, right? So there's a uniform path here, here, and here. So any vertex here is disjoint from some guy there or some guy there. This is what we proved earlier. If it's there, then you go straight to X. If it's there, then you go straight to Y. So for any vertex in this guy, I can get to x or y in 2 steps. Diameter is most likely. Okay, so we just checked the criterion. So the arc and curve graph is uniformly hyperbolic, where the boundary of the surface is non-empty. So you'll get the result for the curve graph when the boundary is non-empty too. And then the last bit's just a trick. So for closed S, there's a forgetful map. And the curve graph of the once punctured G surface. The curve graph of the closed surface of G. And this is 1 Lipschitz. So first of all, important property is 1 Lipschitz. The next important property is that there exist sections to this projection. And any such section will be my isometry, because it's the 1 Lipschitz map. So if this is delta hyperbolic, then that's delta hyperbolic. Because you can lift any geodesic triangle. Still this in there, and then push it down. Okay. How are we doing for time? Pretty good. Oh yeah, so we're done, by the way. just to make it clear, we're done. Right? Subsurface projection, okay. So I finished like first half of the talk talking about these arc and curve graphs. Now we're going to talk about subsurface projection with Tarek. Well, it's a very useful tool. So I think this sort of concept first appears in Ivanov. I see people nodding their heads, so that's good. So it was sort of, I don't know, revolutionized by Minsky. Okay, I'll explain why the theorem very soon. Okay, so if I draw the picture of what subsurface projection is. Just to give some motivation. Right. Suppose you've got some subsurface of S. Well, a priori there's some, you can take mapping classes and you can have pseudo-unresolved supported on subsurfaces. So if you want to try and capture that information, how do you do it? Well, you can define subsurface projection for curves into the curve graph of this subsurface. So suppose I have a subsurface Y, and then some vertex. So you can define this for us. Some vertex in A, C less, such that. Yeah, I'll start a new slide. So suppose you've got a vertex with A, C less that cuts Y. You put them in a normal position. So you put X in such a position where it intersects the surface minimally. And then you just take the intersection of X with the subsurface. You get some isotonic classes of stuff in Y. You just take those isotonic classes. And I'm going to call this kappa Y. That's a subset of the arc and curve graph of Y. Okay. If you have any questions, just ask, okay? So here's some facts about kappa Y. First fact is kappa Y is 1 Lipschitz, whenever it's the phi. Okay? So 1 Lipschitz sends paths to paths. Number 2, defined almost everywhere. What does that mean? Well, in other words, it's not defined in a diameter 2 subset. Okay. So it's only not defined in a diameter 2 subset. So if you have any two vertices which miss the boundary, so it's just like this tiny little ball in the whole curve graph which isn't where it's not defined.
Curve graph of what?
S.
Okay.
So yeah, I've got curves on S. I want to project them to the output curve graph of Y. Well, that projection's only not defined on a really tiny small subset.
So image is not an element in the arc curve graph, it's a subset.
It's
Yeah.
a subset, but it's a diameter 1 subset. So really, it's really tiny. So it's a bit like a point. So. I mean, like, this stuff isn't about being really, really exact. We're just doing the coarse geometry. So. Okay, theorem. Masur and Minsky. There's just some constant depending on your surface, such that whenever G is some geodesic in the curve graph of S, okay, Y is a subsurface of S, and last criterion, each vertex of G cuts Y, so the projection is defined. Then the diameter of the projection is at most big. It doesn't depend on the geodesic or the subsurface. As long as each vertex cuts the subsurface. So this is called the bounded geodesic image theorem. Take a geodesic and you project it on an image. Okay. Chris Leininger gave. Chris Leininger has an unpublished proof of this theorem. Right. Well, that's what Saul tells me. Okay. Okay. And recent work of Bowditch. If you combine these two, then you get B that's uniform. So B that's independent of S. Okay. I just want people to know this. Okay? So
sorry, but recent work of Bowditch is not his proof of uniform hyperbolicity.
yeah, so you want to, so this proof goes by using Bowditch's quasi-geodesics. So you take the subsurface and you take some curve and take a Bowditch line to the subsurface, and then the projection of that will be bounded, and then use some hyperbolicity argument to get bounded geodesic motion. So you need to know that these lines are uniformly quasi-geodesic, or that would be unparameterized. So I think you do need Brian's recent one. So this isn't written up in the literature, by the way, because this came. So this is very recent, and I think this is not so recent. Okay, so today I'll show you that you can take B equals 50 if Y is non-annular, and 62 if y is annular. And I'll give you the key idea, and then I'll say somewhere about the proof. So there's
So the Leininger Bowditch proof will presumably give enormous constants because he gets very large constants for the uniform hyperbolicity too. Is that right?
Yeah, so you could use like the small uniform. I would presume so, yeah. But I would say probably 3 digits. I wouldn't say 4. I've not written it down, so I don't know.
Wait, you told me at Will's house it was 98.
Yeah, but this is AC.
That was 2 days ago.
What's that?
It's
Oh,
AC.
it's
So it's 98 AC. Yeah, so very good. Please ask questions. So here's the key ideas. There's a key observation. I just want to say, like, what makes this proof work? Rather than just giving you the proof, I want to give you the picture. So just suppose that the boundary of S is non-empty, and you're given y a subsurface. And the y is a subsurface. Now pick an arc, which I'll call B, because I'm like that, not A. Pick B that misses boundary of y. Pick an arc B that misses boundary of y. And let A be any other arc. Any other arc. So there's some setup, but I'll draw a picture and hopefully we'll simplify all this stuff. So suppose V is a unicorn arc from A to B, and the distance in the arc and curve graph of S between V and the boundary is at least 6. Okay? So I'll go B3. This here is just to make sure that this guy intersects this guy enough. That's what's in C. And the conclusion is that when you project V and you project A, they have a common arc. You can't see that, I'm just shouting. So let me just draw a picture in AC, the graph. So here's the picture. You've got the boundary of y here. Okay? Maybe I should make this bigger. And there's always some arc, which is disjoint from the boundary of y. It could be in the subsurface, but that's okay. And then you get any other arc A, right?
Okay, the boundary y does not include the boundary of X.
No.
By definition.
Sorry, right, so I will say there is some Morley curve associated with boundary.
So the part that's not on the boundary of X.
So really, I mean, when I say boundary y, I really mean like as vertices in the arc and curve. Thank you for clarifying that. Okay, so take this arc, that's disjoint from boundary. Any other arc, and you've got some equal path, and there's some v here, and the distance from v to boundary is enough. Okay, so let's just do the proof now of why this is true, and it's true because okay, so it's true because so let me just draw a picture of the surface. Let me draw a picture of V. Okay? Picture of V. So V is a combination of the arc B, a subarc of B, and a subarc of A. Sorry. Okay. Is V. Now, the intersection number of V, the boundary of the subsurface has to be at least 3. And that follows from this distance boundary. So the intersection between V and the boundary of Y is at least 3. Where must the intersections be? They can't be in B because B is disjoint from the boundary. So it must be in A. But now, one of these bits has to be inside Y. And then that is the common arc. Okay? So that's how the arc exists. Now, some of the experts in this audience might be like, yeah, we're done now. But I'm going to tell you the rest of the proof. So I'm going to restrict myself to a subcase first. So I'm just going to call this the baby case. It's not really a baby case, but I couldn't think of another word. It's just a subcase. Okay. So suppose G is a geodesic of the curved graph of S. Okay? Right? Very good. But also I want to assume the following. So we're getting into the proof now. Okay. So suppose I have the following. The distance from the geodesic, the nearest, the smallest distance from a point on the geodesic, the boundary of Y, suppose that it's at least, okay, the distance is perfect. Actually, suppose it's at least 22 for reasons which we'll soon get to. Okay, it'll turn out to be 22. Okay, and then, so the claim is that the diameter of the projection of Y, or the projection of G to Y, is most 3. Okay. So I'm going to show you how to do this now. So 3 is a bit surprising. But remember the geodesic is quite far away. Okay, so let me prove the claim. Suppose C and C prime are vertices of G, okay, any vertices. Then take the sub-geodesic of G. So this is in G, so this is a subset of G. Okay, that's the sub-geodesic of G from C to C. That's still at least 12 from the boundary of Y. Okay, and now take any arc A adjacent from C, any arc A prime adjacent from C prime, and then take a uniform path. Okay, so this is P of A plus A minus. So I'm not writing all this down, I'm just saying what to do. Okay, and you've got the boundary of the subsurface down here. In the graph. And you've got B. Okay? So take the uniform path to B, here and here. Right? Okay, so now there are some claims. Number 1, there exists a clique. Okay, I'll draw the clique. There's a clique like this. It's a triple of uniform arcs, which all miss, and there's one on each side. So this is done in our paper. Sebastian Hensel, okay, and then number 2. So I'm sorry for this compactness here. Number 2 is that the distance from V prime to G in AC is at most 8. Right. And now this baby case, sorry, this key idea will start to come into play now. So this is also in on paper. Okay. Right. So now, by the assumption, the distance of V to the boundary of Y is at least 12 minus 9. Which is 3. So this guy is far away from the boundary Y. It's at least 12. Oh, I forgot to mention that. Yeah, sorry about that. This assumption here, this assumption here implies that the distance in AC from the geodesic to the boundary Y is at least 12. Yes, it is 12, not 14. So distance from V, boundary Y, has to be at least 12 minus 9, which is 3. And why is that? Because this geodesic is really far, but V is close to the geodesic, so it has to be really far too. Okay. Now, like key idea. So there exists some arc, which is in the, which is shared by both A and B, and there's some arc A prime. Which is shared by both this guy and this guy. So now I go, so if I take C, then I go to A, then I go to A prime, then I go to Y. So I project this guy, and then this is adjacent to this. This share an arc. That's disjoint to that. These share an arc. And you get to that guy. So through. Okay.
Where are A and A prime again? Capital A, capital A prime.
So that's in the. So remember the key idea said that there is a common arc.
Right, but in this picture, where
Well, you started with curves and then you went to arcs.
What's the question?
where are capital A and capital A prime in this picture?
So capital
Are they
A
actually on the side?
lives in the arc and curve graph of Y. So it might not necessarily correspond to
they
anything
don't actually
else.
appear in this picture, maybe.
No, so for example, A could be an arc with its endpoints on some curve in S.
Okay.
Like, so for example, boundary of S, so the boundary of Y could be a curve,
Right.
and then this guy could have endpoints on. So it might not be anything in S. Okay, and now we're actually done for the theorem now, because G is a geodesic. So, so the general case, quickly, general case, you have some geodesic G, and the boundary Y here. So you take the tails off here, take the tails, okay? And so the baby case will apply to these tails, because G is a geodesic. It can't hang around forever, the boundary Y. It has to go away from Y. And then this bit here I can't control, but I know its length will be at most 44. Okay? So if I'm given any vertex, I could get from here to here for 3, and then go along here 44, and go here to here in 3, so that makes 50. Okay. That's good to get to the basics. So I have 4 minutes left. If anyone wants to argue with that, well, feel free. But I'm going to tell you, just apart from like the applications included in hierarchy machinery, there's other applications in order to get effective versions of theorems. So here's one which doesn't use hierarchy machinery, as do Mangas. So one application is to make effective version of the following theorem, which is due to Mangas. And I really like this theorem. And I'm going to say just one of the things she does in it. And it says that given S, there is some constant K, independing on S, such that whenever A is some set of a mapping class group, and the subgroup generated by A contains a pseudo-anisotropy, then in fact there is a pseudo-anisotropy with a short word length in terms of the elements of A. And in fact, A doesn't need to be finite. Okay, so what's K? Well, if you look at the Humphreys generators, then you see that K has to be at least some linear function. Because, if you have Dane twists, you only have, 3 of them allowed to make a pseudo-anisotropy. You're going to miss something in the subset, and then you're going to miss something in the surface. So you can't have a pseudo-anisotropy. So K must be linear in the context of surface. But I'll tell you something. Suppose A contains an infinite element. Then you can take K to be some exponential of the surface, or conversely of the surface. Okay. And I really don't know the answer to this question. What could K be? And I'll stop there.